This is work from a multidisciplinary team at BYU, and also we've had the good fortune to work with Robert Lang, who's made a profound impact in all of the work that we've done in this area, and you'll see a lot of that here as well. And we're going to talk mostly about applications. So we've done a lot of fundamentals in the research, and that allows us to do the applications. But the hope here is that this will provide some inspiration for your own work. So I hope you'll have a pen out, and as thoughts hit you, that you'll just jot some of those down. We'll go through some of it fairly quickly. So first, a little bit of a background, and then the applications. So first, the Compliant Mechanisms Research Group. Our mission is to make an impact by creating compliant mechanism theory and applications that are novel, used by others, and make a difference for good. And hopefully you'll see some of that here. But first of all, what the blazes is a compliant mechanism, you're wondering. And so here's a traditional mechanism where you use hinges or bearings to get your motion. And you guys at Cornell have an amazing display of Rouleau's mechanisms over here. I went and walked through last night. And this, though, is a compliant mechanism. So now I'm going to get my motion from flexibility or deflection of flexible components. And so you can see some big advantages of going to a compliant mechanism, right? I can get rid of friction and wear, get rid of bearings and hinges, eliminate the need for assembly. I can make things at the microscopic scale. So we worked in the MEMS area for a number of years. These could be single-walled carbon nanotubes, if only we could figure out how to attach them all, you know. And so it gives you a lot of opportunities. And then, of course, we discovered that origami is a compliant mechanism, right? Because I'm getting my flexibility, my deflections from the deflection of paper. So this is what we call an origami water bomb base. And this very simple structure that leads to other origami models, okay, but it has some really interesting properties. For instance, it has 2 stable equilibrium positions. And so we can learn a lot even from these simple structures like this. And including this has what we call property of being rigidly foldable, which means that all of its motion can happen just by flexibility of those creases. And we can demonstrate that by showing here rigid panels with literal hinges at these positions. And the other nice thing with this is this gives us a way now to mathematically model these behaviors and emotions. And so that demonstrates that, but I really still like the single layer properties of origami and paper, but I need to go into other materials, and here I'll use what we call a surrogate fold or a surrogate crease, and to get that motion. So now if we look at a little animation here of a degree 4 vertex in origami, and we treat each one of those as a hinge joint to intersect at a single point, that becomes what we call a spherical mechanism that, again, we can create our mathematical models and determine the motion and everything here. And so there's a lot of research to be done in this area of origami-based engineering. You know, how do we move to other materials, getting deployable surfaces? And I'll just mention 3 in a little bit more detail. One of these is thick origami, and our work with Robert Lang, he showed a little bit there. But now, as soon as I go to another material and have some thickness, you know, the nice thing with paper is it turns out it's paper thin, right? And as soon as I go to something else, I have to modify the crease pattern in order to get the motion that I want. There's also this idea of rigid foldability. If I can control this, it makes my mathematical modeling and optimization easier. And this idea of surrogate folds. So let me just demonstrate that in another simple thing. It's a degree 4 vertex in paper. It's rigidly foldable, and which means that this could have its motion all with just motion at the creases. Now let's say I wanted to go to something like polypropylene. So 1/8 inch thick, okay, very stiff. I'm not folding that, right? And so I need to find other ways to do that. And here's a simple example of getting that same kind of motion that I have in that vertex. Now I put surrogate folds now at those places, and that piece of polypropylene folds up. I also have to accommodate the thickness because now I've got a 1/4 inch of polypropylene in there, and this has a very simple thickness accommodation technique that you can see that this surrogate fold is much wider than the others that allows that to come in. And we'll see some other surrogate folds as we go along here. Well, there's some interesting things we can learn from origami. This interaction, every time you start to mix disciplines of this art and engineering and science, and one of the early things we did was look at action origami. And action origami is origami that moves. So if I were to fold, say, a rose or something, that's not action origami. But if I do Jeremy Schaefer's Venus flytrap, for instance, that opens and closes, had kind of a mouth-like motion, that's action origami. So we looked at all the action origami models we could find in the world. Every book, web page, everything, and classified those and tried to find the different mechanisms. And not surprisingly, many things, like whether it's a dinosaur or a Venus flytrap, will have kind of the same basic mechanism and then different art around it. And we could classify these mechanisms. One interesting thing that happened is we found different ways of obtaining new kinds of motion that we would not have gotten to using our traditional engineering approaches. And that's a really interesting thing that we get from this combination with this art. I'm going to show one other example of this concept. So I wrote a book on compliant mechanisms, and this is how interesting that book is, okay? But in that book, I make this comment that a compliant link cannot produce a continuous rotational joint. And that's pretty obvious, right? You don't need any mathematical proof to tell you that, a traditional mechanism, right, I could put a motor on there and have it rotate, right? And so that's pretty straightforward limitation. But no one bothered to tell the paper folders this, okay? And they created the kaleidocycle. So this kaleidocycle has continuous rotation, okay, where these joints, none of them are going, even though the whole system is going through continuous rotation, no individual link is, or joint is. Is that not freaky? Okay, so, and then, of course, we wanted to move into other materials. And here it is with surrogate folds, but in polypropylene. And so, again, we have a polypropylene mechanism, one chunk that can go through continuous revolution. And then this is the same thing, but now in acrylic, which is a very brittle material, but we can still do that. And acrylic is nice because it laser cuts so well. And so, anyway, you can come look at these during the lunch break here. Okay, so now let's look at some applications. So we're going to start out with some applications in space, things we've done with NASA. And it turns out that origami in space has the same advantage as the compliant mechanisms in space. We get rid of the friction, the need for lubrication, we can reduce weight, but we can also make things very compact, deployable, and which has some real advantages in space. So we'll look at solar array. Paul showed an animation of this a little earlier. We'll see where this comes from. This was with Robert Lang and JPL. And the goal was to create a solar array that had 250 kilowatts. Put that in context, that's double all of the solar panels on the International Space Station combined. And if you were to make that in a circular thing, that's 500 square meters, which would cover 5 lanes of traffic. Okay, so it's not something you can launch into space, and it needs to stow into a standard launch vehicle. And we're designing for the Atlas V, and This took a lot of mathematics and other things to get it changes the crease pattern. Robert Lang did a lot of the math and stuff to make this all work out. This is a 20-to-1 scale prototype. And these are Garolite, fiberglass panels capped on membranes. This is what we call for our surrogate folds, what we call a membrane fold here. And then also had the different thickness accommodation technique there. And it turns out this hole in the middle is convenient because that's where you put the spacecraft. And this is similar to this is the same animation we saw a little earlier here, but you'll also, if you look close, you can see what's called the perimeter truss that's deploying this, which wasn't necessarily our favorite way to deploy it, but NASA has heritage in that area. Okay, another one. This is with NASA Marshall Space Center in Huntsville. And this I want to show you because it shows something where we use paper to help us in the design, but then in the end, it's a mechanism that's not flat at all. It actually starts out flat, but then has a 3D structure. And so it can still be inspiration either for other things. So this is a 2 degree of freedom pointer mechanism. So let's say I wanted to be able to point this laser anywhere in 2 degrees of freedom. Okay, and but I wanted to also be able to do this without any friction or wear, not have any pinch points for fuel lines and so on, and have very low mass, get rid of some of the actuation. So here's the great thing with paper, is the prototyping is cheap, right? I could go through a lot of prototypes really quick. I walk over to the recycle bin, pull out a piece of paper, and off I go. And here are a couple of early prototypes of this, which eventually needs to end up in titanium. Also, we have, once we do the mathematical models and things as well, then to work out the interfaces, we have our own set of custom compliant mechanism Legos that we work with to prototype. And then once we're starting into weird geometry, numerical models using finite element analysis. And then this is a 3D printed version in a polymer. We needed to get to titanium for space grade materials, and here's some individual components at that. And then the final crazy looking beast, 3D printed in titanium. And everything on there has a purpose and a function, okay, which is kind of hard to believe until you see it. But notice these areas that have these kind of X's. Okay, those are surrogate folds that look like this. This is cross-axis flexural pivots, often used in precision instruments. And so those creases you saw in the paper are now replaced with these. And here's the first input to the first rotational axis, input to the second rotational axis. That's where we connect to the spacecraft and then attach with the output stage. This is animation showing this in spacecraft orienting a thruster. And so we get all the bending motion, so no friction or need for lubrication, which are problems in the vacuum, and no pinch points and so on. So this is the same thing, just in a communication satellite, but we'll move on here. Then bellows is another interesting thing. This is again with Jet Propulsion Laboratory and a couple different applications. This is an asteroid redirect mission with these origami bellows potentially going on drills to protect from the debris. And so here you want to drill into an asteroid so you can grab it to bring it closer to Earth. This is on Mars 2020. And so here, getting these in space grade materials with the fatigue life and everything we need. So here are the traditional metal bellows that they're using that are very stiff and heavy, and dramatic difference here when we do an origami bellows in a space grade polymers or other materials. And it can make a dramatic reduction in the mass, not just in the bellows themselves, but when I can have this kind of compression ratio, it also dramatically reduces the amount of structure that it takes, all the shafts and everything else. And so Okay, so those are the space applications. Now let's move into terrestrial applications and start with some biomedical origami. And first one is in collaboration with microbiology of looking at new ways of doing genetic research, of injecting genes and finding what different genes do. So it turns out DNA has a net negative charge. So we have a lance with a positive charge to attract the DNA, put this into a mouse egg cell, reverse the polarity, and release the DNA. Now, if you do this while the male and female DNA are mixing, you can introduce your gene into this into the genome here, and you take that cell, put it into a surrogate mother. Cell divides until it becomes a baby mouse, and hopefully it has your gene in it. You can see what that gene does. And so here's an early prototype of the device. This is a scanning electron micrograph. This is a latex sphere representing the cell. And holding devices is similar to pop-up mechanisms. We also have to maintain electrical contact through all these through the motion. And this is computer animation showing this 2 stages of motion. First stage to pop up, and then to come over because you don't want a ripping motion to rip the cell. You have to not only hit the cell, but the pronucleus within the cell. So high precision motion. And we have demonstrated that this works. And you do that by putting in a gene from a jellyfish that makes the mouse grow green in the dark. So no one can deny that you got it in because the mouse grows green in the dark, right? And so there are other ways of doing that, of injecting genes, but our data shows that this looks like it's going to be dramatically more efficient than other methods. So, and this is SEM of another version here where we've made polycrystalline silicon hinges. So again, another brittle material, but we can still do that just like we did here with the acrylic of having the geometry right. Another one, we're working with a company called Intuitive Surgical that does the Da Vinci surgical robot. And the idea with minimally invasive surgery is I can make a very small incision, go into the body, and then with our origami things expand out and do more complex surgical tasks. And the nice thing with that is it turns out you got plenty of room inside because they blow up your gut with CO2. It's like you're 10 months pregnant. And so people wonder why their shoulder hurts or whatever after minimally invasive surgeries, because all that CO2 is making its way through your body sometimes. But anyway, but you want to minimize the incision size. Here's what we call oriceps, okay, which is based on the origami chomper mechanism. But again, one piece, but also has this nice property that can be very small, come in this way. And this is larger than the actual device, right? But come in and then can morph into the oriceps. And so here's an animation showing this. It looks kind of like a Toontown thing, but this is actually what surgeons use to practice minimally invasive surgery. We'll show another one. It's in a surgery. It's just an animation, but if you're queasy, you might want to look at the floor for a minute. See it, oriceps will come in, deploy, morph into the gripper mechanism. In this case, it's just moving liver around to perform another function. And let's see. And then this is with GE Healthcare. We did some more bellows, kind of like in space, but in this case with sterile materials using Tyvek and other materials that can be used there. But in interest of time, we'll move on here. Consumer products, another interesting place to have a lot of applications. And this is mostly with group and industrial design. And I'll just show you a couple of their applications here. One is backpacks. And here you can see her paper models. Okay, and these can compress and be small. And there's your prototype backpack. And so when it's not in use, this compresses very small. This is called the tessel jetpack, where here this origami tessellation Has no other purpose other than it looks cool, okay? And, but it does look cool. They call it the jetpack, okay? And these students on this team put this on Kickstarter. They more than tripled their funding goal, sold lots of these, and actually are now being knocked off by other people, which I guess is the greatest form of flattery. But here's another one from them. And this I'm going to show because it uses a manufacturing process that's interesting. You'll see parallels to what you do at the micro level with masking and stuff, but it's still, you see it at the, another way of doing this and another reason to do this. And this is making furniture out of felt. Okay, and here he is masking these areas where he wants the surrogate fold. Okay, and then with that mess, and then puts a resin everywhere else to stiffen it up. Okay, so it's still the same material everywhere, but with the resin added in some places. Then it folds up into a very compact shape, expands out into a stool, and there it is in use. And okay, so far we've shown applications in space and biomedical applications and consumer products. And I'm going to show you 2 other applications that I don't know how to classify other than saying they're surprising that you would use origami to do these. Okay? And the first one is bulletproof origami. Okay? And so this is, imagine a bulletproof barrier that a police officer can make very compact, store in their vehicle, and when it's needed, it deploys out. Okay, so this is made out of Kevlar. We'll see places where there are surrogate folds here and other material in the Kevlar. But it is continuous layers of Kevlar. So here you see a high-speed camera showing the bullet interacting here. The deployment is very quick. And again, high-speed image here. Early prototypes, everything from wood and fiberglass. Of course, started out with paper and then cardstock, fiberglass, wood. And you can see a better video of this online if you just do bulletproof origami. But here you see 12 layers of Kevlar with some panels in the middle just to give it stiffness, ballistic nylon on the outside to protect the Kevlar from the environment. And police officer deploying that. And here's another prototype in just the foam board. That. So here this is shown with a single officer, but it was really original design was with SWAT, where as you see the SWAT guys demo this. They'll have one guy in the middle that's the armor bearer, and then 2 guys on the side that are armed. And so we'll have smaller versions of this as well for single officers. So. Okay, so another surprising one is origami on freight locomotives. Okay, so it turns out that a freight locomotive is like a brick going down the tracks. Okay, horrible aerodynamics. You'd love to put a nose cone on them. The problem why you can't put a nose cone on a freight locomotive is because they're like a Lego block. You never know where they're going to be in the train. And so it has, whatever you do has to be compressible. And so here, this is in collaboration with our fluid dynamics group and with a company that likes to remain anonymous. Here's a early prototype. A lot of mathematical modeling and things going into this. This is what we call non-developable origami, and that there's no place where it's a flat sheet. A lot of computational fluid dynamics to optimize it. Not a shape we would have come up with on our own, but this is what the wind tunnel tests and CFD says will work. Be deployed very quickly. You have to, when it's stowed, you have to have this opening. That's how engineers actually walk between these while it's moving, which I did not know. But anyway, our models show that this will save about $2 million per year in diesel per 1,000 trains. And the company we're working with runs about 3,000 trains. So that's $6 million a year in diesel plus all the emissions and the CO2 and everything. is being saved there. So, well, as we look at those, it makes you wonder, what else does the future hold, right? What's going to happen? The fundamentals we're looking at, there is still a lot of work to be done. And the applications are just infinite. If you look at the variety that we've just seen here today, and now think of what else is possible, it's just stunning. And it's exciting. And I'd like to acknowledge, of course, all this work is really done by the students back in the lab. And appreciate funding from NSF and AFOSR and NASA and the companies that have supported us and collaborators that we work with. And thank you. And I cut about 10 minutes out last night when I realized I was between you and lunch. And I thought, yeah.
For your micro cell injector, you said that was made from silicon sheets. What was the compliant material between the silicon? How was that assembled?
You know, that is all polycrystalline silicon. And so it was made just using, different layers of silicon with oxide layers in between that we released. And the early prototype I showed you actually really had hinges where there were pieces that were in there and then just moved with a fair amount of friction and quite a bit of clearance. And then the later version was just polycrystalline silicon, but the geometry was such that we could make it, even though it was brittle material, we can make it flexible, but there's zero tolerance to overstress, right? Because when silicon overstresses, it just explodes. So,
So a question, like in one of these applications, you go in and there's sort of two parts to it. There's the design of the structure and the way the origami is going to work, and then there's also the materials aspects of it, choosing the right material, et cetera, et cetera. Which is the bigger, the more challenging part? How do they relate to each other, et cetera?
yeah, so that's a good question. And one of the things that makes compliant mechanisms in general complex, in addition to the origami things, is here, when I make this is totally independent of the properties, right? And now here, they're very highly coupled. And so everything, that coupling now makes everything more complex because the kinematics and what the behavior is highly coupled to the material properties. And so when I was using hinges like on the freight locomotive, that I could decouple it. And they needed steel because there's all kinds of impacts coming and stuff. And so that just has traditional hinges on it. But now at the micro level, you're just stuck with what you can make, right? And so we don't like silicon really for a compliant mechanism. I mean, you don't want to use that, but that's what we could do. And so yeah, that coupling is a big challenge. And then, of course, with the bulletproof origami, right? That was Kevlar. We could use other materials and stuff too. But I forgot to mention, if you want to see what bullets look like after origami stops them, you can come up. And there's a 9mm, 357 Magnum, and 44 Magnum bullets there. So, okay, great questions. Anything else?
Yeah.
Oh, okay.
I understand that the fold patterns are copyright protectable, and so how much barrier is there to these kinds of commercialization projects to develop a novel folding pattern to even make a Kevlar barrier?
Okay, so yeah, and Robert can maybe step in here as well. Why don't you go ahead? I saw him come up out of his seat here, so we'll let him.
So copyright only protects the artistic aspect of something. So, and functionality is not protected by copyright. That has to be protected by patents. And there's very few patents on origami structure. There are some, and so that's an issue, just as there's patents on probably anything else that the professors here do and try to patent. But because a lot of these fold patterns are out and have been out in the public domain for a long time, the available patent protection is usually fairly narrow, because it has to be combined in some novel concept.
Okay, good questions.
That's actually a really good point, because oftentimes technologies can get really bogged down when the field is over-patented. And I think, in the semiconductor industry, there was some sort of sweet spot that people found where companies still made money, but progress could still be made by borrowing and stealing from different people. And I think origami, devices and technologies are in that sort of category.
I'm actually surprised there's not more patents. For example, on automobile tires, every possible tire groove design you could ever imagine is patented. Same with the groove designs in polishing pads; those are all patented. I was guessing origami would be the same way, that every new origami type would be patented, or even as an improvement, a subtle improvement on whatever else was already on there.
I suspect one big factor is that patenting costs $5,000 to $10,000 per patent, and so you need a commercial application with well over that amount of profit. And thus far, there haven't been those. I suspect with the evolution of origami into technology over the next 10 years, or the past 10 years and now, that there will probably be more. But it got a late start.
Yeah, so most of these devices I showed here today are patented as far as the devices, and they've been either licensed or under option to companies, with the exception of the folded furniture. And but that's just on the specific device, not on the pattern in general. So.
Okay, I want to make a couple. Well, first of all, let's thank Larry once again.